This educational film is about ELE361, which is electrical machinery course, and I plan to present the solution of an example from the textbook of S.C. Chapman, named or entitled Electrical Machinery Fundamentals, printed in 1999 in the 3rd edition. Problem 221 on page 128 states that prove that the three-phase system of voltages on the secondary of the delta Y transformer shown in figure 2-38C lags the three-phase system of voltages on the primary of the transformer by 30 degrees. So let's revisit figure 2-38C. It's on page 112. Primary and secondary side of a transformer is given, and the primary internal connection is delta, secondary connection is Y, and line-to-line voltages and phase voltages are as shown. So for the secondary side, phase voltage is here across each coil, and line-to-line voltage is shown as here. Phase voltages are shown with letter phi in the subscript. Line voltages are shown with letter L in the subscript. There is a turns ratio between the sides, or between the primary and the secondary, regarding the number of turns in the primary over the number of turns in the secondary, and they are identical for all three phases. Now let's look at the solution. The system of voltages include line-to-line voltages. So the problem is about making a proof between the line-to-line voltages in the primary and secondary. So we first express everything in line-to-line voltages. The system is assumed to be well balanced. Well balanced means all the line currents and phase voltages are equal, but they do have phase separation, and the phase and line voltage phasors do have identical 120 degrees angular separation in their functions. So we'll consider the primary side, express these voltages. In the primary side, we do have delta connection, so line voltages and phase voltages are identical, and they are shown with some amplitude times cosine functions with 0, 120 and 240 degrees separation. So the phasors are equiangularly separated in the domain. At the secondary side, phase voltage at the secondary is Y connected. Turns ratio times the primary, or N times line to line voltages at the primary for all three phases, N times the amplitude and cosine functions. They are delta connected. Primary phase and line voltages are equal. Secondary phase and line voltages should be defined. The phase voltages at the secondary will be given as turns ratio times amplitude times cosines, and these three phasors are separated by 120 degrees separation. Let's determine line voltages at the secondary side, because these are phase voltages. So this is the set of phase voltages. Line voltages will be the difference of the phases. For the first line-to-line voltage, this is the difference of the first and second phase. So the difference is some amplitude with turns ratio and difference of two cosine functions. We can use a trigonometric identity of 2 sine alpha times sine beta equals to cosine alpha minus beta minus cosine alpha plus beta. So this is very similar to that side. Alpha and beta can be defined alpha is omega t plus 60, beta is 60. So this is alpha minus beta, angle is 0, alpha plus beta, angle is 120 degrees. So if you rewrite, okay, by using this equation, the line voltage is simplified. The subtraction of the cosines are eliminated. We only have multiplication. And sine 60 degrees can be written by its numerical form. So we do have a very simple sine function with amplitude. Here the turns ratio n has been forgotten, so let's add n here. Okay, now it's perfect. And a simple sine function, or equivalently a cosine function with 30 degree phase difference, is the final result. So similar derivations may be held for the second line voltage and the third line voltage. So the whole set of line voltages can be expressed as this. We only should add n times Vm here because those terms are forgotten. So this is the n is the turns ratio, Vm is the amplitude of the phase voltage, and square root of 3 comes from line to line voltage separation. So apart from this constant square root of 3, all these functions are only different by their phase relations. So the primary side line voltages are expressed in this 3-element set, and secondary side line-to-line voltages are expressed in this 3-element set. You see that the angle separation is for the, corresponding to the same phase is 30 degrees, and similarly for all voltage pairs the separation is 30 degrees. So proof is complete for this problem. So this is the same expression, only we do have n to count for the turns ratio.